3, rigid vessel. So that means volume's not going to change. Anytime you see the word rigid vessel, it's fixed volume. It says the volume's 2.5 meters cubed, and it's got 5 kilograms of a saturated liquid vapor mixture at 75 degrees. This is water. So now the water's heated slowly. We want to know the temperature at the point in which the last drop of liquid vaporizes. So that would mean all of the mass in the system is vapor, but it's just at the other edge of saturation. And so that would mean we have saturated vapor. So we know, we can say at state time 1, we have certain conditions, and at time 2, we have other conditions. Okay? So let's see things we know at time 1 and 2. So at time 1, we know that the volume's 2.5 meters cubed. We also know at time 2, it's 2.5 meters cubed also, right? That was a rigid vessel. 5 kilograms, that didn't change. It didn't say anything about water coming in, water leaving. So we have 5 kilograms at both states too. It says initially we have a liquid vapor mixture at 75 degrees C. So that was time 1. So now we're going to heat the water. We want to know the temperature at saturation, right? So by knowing saturated vapor, that defines the state at 2. Saturated vapor and saturated liquid, those things are sort of fixed. They define the state. If we said there was a saturated mixture, that wouldn't do us any good because we would need to know how much was vapor, how much was liquid. Saturated liquid, we know all of it's liquid, and we can use that in the tables. Let's see. Determine the temperature. I guess that's about it. And really, the trick here is what we're looking for is T2. And so what we're trying to do is define the state at 2. Find the 2 properties that fix the state at 2, and then we're going to use our property tables to get the temperature. T2 is our question. And so here we're going to do the same thing as we did in problem 2. We're going to use specific volume because we know the volume, we know the mass. We can get specific volume. We know the fact that it's saturated vapor, and so we'll use those in the tables. So specific volume. Volume over mass, 2.5 meters cubed over 5 kilograms. So that's what, 1/2, 0.5 meters cubed per kilogram in saturated vapor. So those 2 things. So this is a little bit tricky because we are looking at the saturated table and we don't know temperature or pressure. The only thing we know is our specific volume is that value, and it's saturated vapor. So we can tell that this value has to be Vg, because that's the specific volume of saturated vapor. This is water, so go back to either the temperature or pressure table. Might as well do the one organized by temperature, because that's the property we're looking for. Doesn't matter, the tables have the same data, they're just organized in different ways. So let's look for Vg, and if you go down, 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 it looks like it crosses, you know, we got 0.0508 at 140 degrees and 0.446 at 145. So we know that it's in between there, and it's much closer to 140, right? It's probably 141 or less. So we'll say T2, approximately 140 degrees C. That's it. That had to be our specific volume, and it's saturated vapor.